Hello everyone, welcome to Metallurgy Gate by C. Patel. Today we'll discuss a very important topic that is related to adiabatic flame temperature. So I have got the question which was asked in GATE 2017 and I will solve one more question which was asked in GATE 2009 related to flame temperature. So the question is, a stoichiometric mixture of CO and pure oxygen at 1 atm and 25 degrees centigrade flows into a combustion chamber. The molar flow rate of CO entering the reactor is 1 kg per mole, 1 kg mole per hour. The adiabatic flame temperature in Kelvin for the combustion of CO with stoichiometric oxygen is dash. This is a numerical type question. We have given delta H naught for 298 Kelvin for the reaction CO2 conversion is minus 282,000 kilojoule kg mole per CO per mole, and the heat capacity of CO2 is given as 44 kilojoule kg mole Kelvin. Now, first we will try to understand what is adiabatic flame temperature. Adiabatic flame temperatures here, you can see here, you can assume here according to combustion. This concept about the adiabatic flame temperature is applied to combustion, and whenever a combustion takes place, there is release of some energy, and release of energy is such that it is assumed to be contained in a box. Here combustion is taking place, you can see here combustion is taking place, and there is no heat which is flowing out of this box, and since there is no heat flowing out of this box, so you can assume here the enthalpy change is 0. Now we'll consider this example only. We have given according to the question that is CO plus O2 is giving CO2. Now we need to first balance the oxygen, 1 3 and here 2, so we will put here half oxygen. So this is the complete reaction. Now in the question also we have been given the molar flow rate of CO entering the reactor is 1 kg mole per hour, means 1 kg mole of CO reacts with O2 to give CO2. According to this mole balance, 1 mole of CO gives 1 mole of CO2. So 1 kg mole of CO will also give 1 kg mole of CO2, and the consumption of O2 will be 0.25 kg mole for O2 consumption. Okay. Next is adiabatic flame temperature, and in this adiabatic flame temperature is basically defined in the terms of the temperature of the product, after the reaction. We'll assume here from the reactant and the product, the reactant is at temperature T1 and the product is at temperature T2 or Tf, that is the adiabatic flame temperature. At T1 we have the reactant 1 mole of CO and zero point 0.5 mole of O2. At the product we have got TF and 1 mole of CO2 is formed, and delta H for this process is 0, and delta H is adiabatic at constant heat. Now, since enthalpy change is a state function, so we can assume it, or we can make it too simple. We can derive it in terms of two stages, delta H1 and delta H2. The path from T1 to T2 can be from this direction also, it doesn't matter. So this is to make it easy. Now, whenever the reaction starts, this reactants will convert to product. So at this point, at temperature T1, and that is given here as the room temperature, that is the 298 Kelvin. At 298 Kelvin, the heat of reaction is delta H1, and whenever the reaction will start, there will be a release of some energy, and the same energy at this constant temperature will be transferred for delta H2 to the product. So reactant to product. So this energy at 298 Kelvin will be given to the product to increase its energy, and during increase of this energy, the temperature of the product temperature will increase. When temperature will increase, that equation can also be related with heat capacity. We know the heat absorbed is also written in the terms of Cp dt, and here Cp is heat capacity per mole, so we'll multiply here number of moles, and in many cases there may be more than one combustion product, like here we have got only CO2, but maybe some other H2 or other in some cases CO2, maybe here H2 or other, so we'll generalize this. This is sigma, addition of all product CPs. Okay, so we have here delta H equal to delta H1 plus delta H2, and this delta H1 plus delta H2 is equal to 0. So this implies delta H1 plus sigma n Cp dt is equal to 0. This implies delta H1 is equal to minus delta H1 equal to sigma n Cp dt. So putting in the equation, we have got delta H1 as this. Delta H1, this is delta H1 which is given over here, and Cp of CO2 is 44 kilojoule. So minus 282,000 is equal to n. N is the number of mole. In the question we have been given that 1 kg mole of CO is being passed, so this will give 1 kg mole of CO2 also, so we use this. Okay, so n is 1, Cp is 44 into dt. dt is the T final minus 298 Kelvin. Okay, so on solving this, you will get Tf is equal to 6707 Kelvin, and this is the answer. So here you need to remember the concept is that the delta H for the complete combustion is 0 at constant temperature at constant pressure, uh, and in adiabatic condition delta H is 0, and delta H will be combination of delta H1 and delta H2. Delta H1 is the heat of reaction at 298 Kelvin. So this heat of reaction at 298 is equal to the heat absorbed by the product to increase the temperature, and this increase in temperature will be related to CPDT. So after this equation you will find this TF, and this TF will be the adiabatic flame temperature. Now I will discuss the another question which was asked in GATE 2009. For this question, for the following reaction at 300 Kelvin, CH4 plus 2O2 gives CO2 plus 2H2O. The heat of reaction is 803 kilojoule per mole of CH4. At 300 Kelvin, CH4 air gas mixture containing the required stoichiometric amount of oxygen is burnt to completion. Assuming air contains 20 volume percent O2 and 80% N2, and the specific heats for CO2, H2O gas and N2 are 50, 40 and 40 joule mole Kelvin respectively, the adiabatic flame temperature will be. So we'll follow the same concept, and here we have got the reaction CH4 plus 2O2 gives CO2 plus H2O. So friends, you can see here we have got here two products. Now according to mole balance, you can see here 1 mole of CH4 requires 2 moles of O2, which will give 1 mole of CO2, and sorry, here it is written as 2 4 4, okay, and gives 2 mole of H2O. Okay, now we already have the heat of reaction at 300 Kelvin. Delta H at 300 Kelvin is equal to 803 kilojoule per mole, and according to all concept we can see the heat of reaction at room temperature 300 Kelvin will be equal to the energy supplied to the product to increase its temperature, and we can find here the products are CO2 and H2O. Now here we have given in the question at 300 Kelvin, CH4 air gas mixture containing the required stoichiometric amount of oxygen is burned to completion. Stoichiometric amount of oxygen is burned, like only 2 mole of oxygen is burned for its completion. There is no excess oxygen which is supplied here. So for 2 moles of oxygen, we need to calculate the amount of air which is present over there, and from the air we need to calculate the number of moles of N2 which is also present, because we are using here air, and air contains both O2 which is 20% and N2 which is 80%. Now we see here air is a mixture of O2 and N2. N2 we have got 20 volume percent, and N2 we have got 80% volume percent. Okay, and here what mole of O2 we are consuming? 2 mole of O2. 2 moles represents 2 mole into 22.4 liter, because 1 mole has got 22.4 liter at room temperature. So here suppose we take air. So air will contain oxygen, suppose let it be X. Then what will be the content of N2? That will be 4x, because it is directly 4 times. It is directly 4 times. We take the ratio, that will be 1:4. Okay, so since here for the amount of air whatever it is taken, we have got 2 mole of O2. So for this 2 mole, there will be 4 into 2 moles of N2. Here you can see here, for X amount of O2 there has to be 4x amount of N2 in air. So for 2 moles of O2, it is definite that 4 into 2 moles of N2 will be present in the air. So that will give out 8 mole of N2. And since for combustion this O2 is used in the form of air, so the O2 from the air is being reacted with CH4 and the left N2 goes into the product. So how many moles of N2 we are getting in the product? That is 8 number of moles. 8 moles of N2. So N2 is also a part of product which is hidden over here. So this is the trick in this question, that N2 is also the product, but since it is hidden, it is coming from this air. So now according to the concept, delta H 300 Kelvin is equal to sigma n Cp dt. So at 300 Kelvin we have been given, okay, so n Cp dt, so n we will consider for, according to the reaction we will consider for first CO2. So n of CO2, Cp CO2 dt is Tf minus 300 Kelvin plus n of H2O, Cp of H2O Tf minus 300 Kelvin plus n of N2 which was hidden over here into Cp of N2 and Tf minus 300 is equal to n of CO2 is equal to 1 mole into Cp of CO2 is given over here. Cp of CO2 is, let me see, it is 50, Tf minus 300, and n of H2O is 2 and Cp is 40, Tf minus 300 plus 8 moles of N2 into Cp is given as 40, Tf minus 300 is equal to T100, 50 plus 80 plus 8 into 4, that is 320. Okay. Now delta H at 300 Kelvin we have given here as 803 kilojoule equal to Tf minus 300 this will come around 320 and 450. So TF will come around TF will come around in this question. We can see here TF will come around 2084 after the solution. Okay, so this is the adiabatic flame temperature for this question. So the answer will be 2084. 2084. This is the answer. So here I think you must have understood regarding the flame temperature, and this is one of the typical question which is asked in GATE. Thank you.